So, my name is Petjan. This work started as an internship project last year, and now I'm continuing it for my master's thesis. It's a collaboration between IBM Research, Jonas from Yorktown, Radu from Zurich, and Animesh from VU University Amsterdam, where I'm a master's student. And so in this research work, we want to answer the question, how do you consume a file system service in a cloud environment? And this is not a simple question because cloud environments are very varied. On top, let me laser pointer. At the top, you see several kinds of servers that might run in a cloud environment where an operator is running their services. There are virtual tenants in containers and VMs, but there are also baremetal tenants. And the question is then, how do you connect these servers to a distributed file system cluster on the bottom? In our view, and for the scope of this research, we think that this solution should satisfy these sets of criteria. It should have good performance. It should have minimal amounts of overhead when providing this performance. It should serve multi-tenancy, which is a core component of a file system, and usually the reason why people consume file systems in a cloud environment. It should be able to support all the kinds of tenants that a cloud environment has. It should be transparent towards the tenant and the client. And the operator should have full control over the system to do management and to do performance optimizations. The attack server should be minimized, and then the network should also be properly isolated from the tenant. In this talk, we present the DPFS framework, which is a DPU-powered file system virtualization framework that uses a DPU in every server to provide the distributed file system cluster to the tenants. And we think that via this system, we can satisfy the criteria. The first option that you might come up with when providing file system services in a cloud would be the traditional approach. So on the bottom, we have our distributed file system cluster with distributed file system nodes. And then on the top, our tenants all run their own distributed file system client. Examples of this are Spectrum, Skrill, Ceph, or Lustre, for example. However, this has many downsides. First of all, this has to be installed, configured, and maintained by the tenant. And especially this configuration part is very difficult. Spectrum Scale, for example, has many knobs, and leaving this to the tenant is not desirable. Secondly, the resource utilization is quite poor. Think of a setup where you have 1,000 virtual tenants, all in their own container, and they would all be running a DFS client, which means that you have 1,000 DFS clients, leading to very poor resource utilization. You would rather want to amortize this into a single DFS client. And thirdly, the security is also quite poor because all of the tenants directly use the DFS client on their machine and then directly connect to the network to the DFS cluster. The second option, and the option that's actually being run in today's cloud, is using an NFS gateway in between. So in this setup, the tenants, instead of running the DFS client, they run an NFS client and then connect to an NFS gateway that sits on top of a DFS client that the cloud operator runs. This NFS gateway then translates these file system operations to the DFS and sends them over the private network. This still has some downsides, notably, again, this NFS client has to be installed, configured, and maintained by the tenant. Now, this is easier than with the DFS client. However, there are still some performance knobs that the tenant needs to turn. And it's especially problematic because NFS is standardized and it's a kernel module in Linux, but it's very hard to innovate on. As a cloud operator, you have very little control over this, which is not desirable for performance optimizations and for management. It is, however, slightly better isolated because now the tenants don't directly go onto the DFS network, but there is still the need for some network access, which is not desirable. So in the recent years, we've been slowly moving towards a DPU-powered cloud, where every server contains a DPU, which is, in a sense, a network interface with some compute and offload capabilities baked on, where the cloud services now run on this DPU. And then they use the networking interface and the offload capabilities in the ASICs to provide these services to the tenants and to accelerate them. Specifically in our work, we focus on DPUs with CPUs, as there are also FPGA-based DPUs. So offloading with DPUs in the cloud is actually being deployed in today's cloud. Notably, block and networking storage is seeing quite some use now, but there's still a lot of opportunity we had with file systems, we think, and this is where DPFS comes in. So with DPFS, we want to provide an abstraction to our tenant on the host. So on the host side, there's an application running unmodified that consumes the file system through the virtual file system in the kernel space, and then should send these commands to some sort of kernel module through some sort of protocol to our DPU. And then on the DPU, we want to implement our actual file system that connects to some remote storage backend. So how will we go about doing this? The stack that DPFS uses is the Virtio-fs stack. And Virtio-fs is an existing Linux kernel module, so there's no need to run specialized distributions or alter the applications. And what Virtio-fs does is it encapsulates the file system operations and puts these over PCIe to our DPU. And this has several advantages. First of all, there's no configuration necessary. Because our file system now lives on the DPU, and Virtio-fs is simply a pass-through of the operations to the DPU, all configuration can be handled by the cloud provider. It works on bare metal because there's no need for the tenant to run any of the operator's code. And it's also fully transparent towards the tenant regarding what kind of file system backend there's actually being run on the DPU. Secondly, Virtio-fs is actually quite lightweight. So in today's cloud, NFS over TCP/IP is being used, and this is a much more complex system than what Virtio-fs is. Using Virtio-fs, now that the file system is completely running on the DPU, this gives the cloud operator maximum flexibility and full control over the actual file system implementation, which allows the operator to do more performance optimizations in terms of fabrics and innovating on the actual distributed file system. The tenant is now also completely isolated from the network because the tenant consumes the file system through the DPU, and only the DPU has access to the network. And lastly, we can support multi-tenancy in Virtio-fs easily. So now that we have our Virtio-fs stack for DPU-powered file systems, the DPFS framework comes in. And there are 3 challenges that DPFS tries to solve. The first one being that providing a file system on the DPU is not standardized. We are currently working with NVIDIA and the NVIDIA BlueField 2, for which we are using the limited technical preview program to access the Virtio-fs feature on the DPU. But we think that if this approach becomes more popular and other vendors start providing this Virtio-fs feature on their DPU, then we will end up in a landscape where each vendor has their own library, and then it becomes very difficult to port your file system to different DPUs. Secondly, building a file system on top of the raw Virtio-fs protocol is quite hard. There are a lot of intricacies in this protocol that you need to keep track of. And so we want to provide an API that's familiar to a file system development. And thirdly, at the moment, it's unknown what the performance characteristics are of this approach and what the design space can contain for using a DPU with file systems. And lastly, we want to use this open source framework to kickstart research and adoption of DPU-powered file systems. We think there's a lot of potential to be had with this approach, and that's why we're open sourcing this framework. So now the DPFS framework architecture. There are 3 layers in the architecture that each try to solve one of the 3 challenges that are introduced in the last slide. So the first architecture layer that sits directly on top of the DPU library is the hardware abstraction layer. And this layer removes the need for the programmer to know the intricacies of their DPU. And it provides a portable base for providing file systems on DPUs. Now, of course, today we only have our NVIDIA Bluefield, but we think that this approach is extensible to other DPUs. The second layer implements a file system API. So if you've ever implemented a user space file system on Linux, then you've probably come across or used libfuse, which is a popular API for this. And we re-implement this API in our DPFS framework so that it's easy for file system developers to port their existing file systems to a DPU-based approach. The API is not fully the same, so a click and compile port is not possible since we made some performance optimizations and choices in the API, but it is almost equal. Now that we have an actual file system API to use, we can start implementing some backends. And the first backend that we implemented was an NFS backend. What this does is it uses the fuse and the hardware abstraction layer to do user space polling on the Virtio-fs device, and then translates these file system operations to user space NFS operations, and then sends them to a remote NFS backend using partial TCP offloading, which is a hardware specialization that's being offered with the NVIDIA Bluefields through the NVIDIA XLAO library. The second backend that we implemented was a key value backend. And the goal of this backend was to show the possibility of specializing your backend based on your workload that's being run on the host side. And for the key value backend, we flatten the tree hierarchy to a key value store, RAM cloud in this case. And we optimize for small IOs and low latency by directly connecting the DPU through RDMA to the remote server. And then the last backend that we implement is the null backend. And this backend is very simple. What it does is when it receives a request, a read or a write, then it just immediately returns this back to the host. And this has no practical functionality, of course. But what it allows you to do is to evaluate the raw performance of the DPU. So this allows you to find out what's the base latency that the DPU incurs, or what's the maximum throughput that is available with your DPU and with the Virtio-fs setup. And this will become especially useful when we will be receiving our new Bluefield 3s, which have 5 ARM generation newer chips and much higher memory bandwidths. So this will be very interesting for them. So those were our backends and the framework. And now to our experiments. So for our experiments, we use the NVIDIA Bluefield 2, which has 8 872 ARM cores. It has 16 gigabytes of DDR4, and then it contains a 100 gigabit ConnectX-6 network interface. We expose the DPU as a single Virtio-fs device to a single bare metal host. Multi-tenancy is something that we are currently still evaluating. So the first question that we would like to answer is, what is the baseline performance of our DPU and of our DPFS setup? And for this, we use the null backend to evaluate the latency and the throughput. With the null backend, we can set a very large QDEF, as we are not running a full file system. But we are constrained to a single core because that's currently only what the framework supports. So on the right, you can see throughput on the y-axis, IO depth on the x-axis. And the first thing that you will notice is that the maximum throughput that we can achieve using this setup is around 8 gigabytes for read and 5 gigabytes for write, where the large block sizes are highly preferred. The second thing that you might notice is the fact that the read performance is much better than the write performance. Currently, this is unknown why this phenomenon is happening. We talked to some NVIDIA engineers, but we couldn't find the solution or the cause just yet. So we are setting it aside as a hardware artifact for now. Using the null backend, we evaluate the latency of the DPU, and this is around 40 microseconds for read and write, where the writes are slightly slower than the reads. The throughput is bottlenecked by the queue depth for large block sizes, which you can see for the 64K block sizes where the queue is full and the throughput stagnates. But for the lower block sizes, the bottleneck really is the slow DPU with the old ARM cores and the low memory bandwidth. The second experimental question that we want to answer is what is the throughput that we can achieve with the NFS backend on the DPU? So comparing the currently used cloud solution to our DPFS framework. On the left, you can see the throughput for 4K block sizes. And here you can see that for the low I/O depths, we are slightly slower, but then for the higher I/O depths, we are faster. And this we attribute to the fact that that on the DPU, we are doing partial TCP offloading, where if you would just be using the host NFS, then you would need to go for the kernel side and then use the kernel TCP, where we do XLAO partial TCP offloading, which speeds TCP up a bit. However, TCP is still the bottleneck here, as this requires a lot of processing on the slow ARM cores. So that is where the bottleneck hits us. Then for the 32K throughput, first we see that for writes, we are keeping up until 4 I/O depth, which is then bottlenecked by our queue being full. But for reads, the performance collapses a bit when we move to 4 I/O depth. And we found that this is because of the partial TCP offloading, which does not work well with the larger block sizes and the higher queue depths. So if one were to further hardware specialize and possibly increase the queue size, which we are also limited on in this case because of XLIO, then we think that we can achieve similar or better performance than NFS, just like with the 4Ks. The third question of our evaluation section is the latencies that come with improving the hardware specialization in our backends. So on the left, you can see the latency that the host NFS solution has, which is around 80-70 microseconds. Then using our NFS DPFS solution, without the hardware specialization, we achieve around 120 microseconds. And then when we add the partial TCP offloading using the XLAO library, the latency decreases to around 95-90 microseconds. On the right, you can then see the latency of the key value implementation, which uses RDMA. And this is even faster. This is faster than doing host-based NFS. And so we think that these latencies are competitive, especially when you take into account that the baseline latency of our DPU is 40 microseconds. So this crossed bar on the bottom, where if you do proper hardware specialization using RDMA with the key value store, for example, the latencies and the throughputs become competitive. In the last part of our evaluation, we want to quantify this claim of the Virtio-fs stack being lighter than the NFS stack on the host. So what we do is we do system-wide profiling for a certain amount of time, then a stress test profiling, and we subtract the two, which leaves us with only the I/O profiling. And then we can calculate how much instructions were spent on this I/O and how good the other performance counters are. And so if you calculate these numbers through, we end up saving 4.4 times the amount of CPU cycles on the host per I/O operation compared to NFS, which confirms our hypothesis that the Virtio-fs stack is much lighter on the host than NFS would be. Now, of course, you are moving these cycles from the host CPU complex to the DPU cores, but because you can now amortize the file system cost, so run a single file system on the DPU compared to running tens or hundreds of file systems on the host CPU. These savings can be very significant. Then to conclude, in this presentation, we present the DPFS framework, which is a holistic solution for today's cloud needs. We can provide around 7 gigabytes of throughput and a base latency of 40 microseconds. And this can be very competitive if proper hardware specialization is done. Our hypothesis of saving CPU cycles turned out to be correct, and we save 4.4 times the amount of CPU cycles on the host. And then for our future work, we are currently working mostly on performance optimizations to make it more competitive. We are implementing IOU ring on the DPU side, which will allow us to consume any kind of file system on the DPU. And we are also working on alleviating this single core constraint that we currently have in the framework. Then we're also further exploring the design space. So we're designing a RPC protocol where we directly put our Virtio-fs commands over the network to a remote site where the actual data is to further improve performance. We're also working on multi-tenancy evaluation. And then lastly, we'll be soon receiving our Bluefield freeze, which will have significantly faster hardware on which we can reevaluate our system. So thank you all for listening. If you would like to know more about the project or get in contact with us, you can find us at github.com/ibm/dpfs. Thanks.
Cool. So we can now invite questions from the audience, either in text form, if you want to put that in chat, or be unmuted and raise your hand, and we can ask questions there. To start this off, I'm always curious when I see statistics, and benchmarks like this about the experimental setup. Do you have any slides or material that shows me, what the hardware and the operating system configuration was at all, so I can get sort of a baseline in my head what you were testing?
Yes, so the setup that we used is
thank you very much.
So we use clean Ubuntu. We remove all the kinds of monitoring and background services that run, which can introduce fluctuations in the measurements. And then we also properly optimize the NFS settings.
Okay, very cool. Thank you. Thank you for having that material. Okay, do we have any other questions for PDI?
I have a question or a comment, more or less. Can you hear me?
Yes, we can hear you.
Yeah. Oh, okay. This on the very last slide, you were mentioning this RPC-based Virtio-fs export, and that seemed to me like the holy grail of virtualization, right? So you don't have any client code left on the client host, and you can basically attach to any networked file system to that approach without running any file system client code on the DPU.
Yeah, so the main reason behind this approach is that we just want to escape the DPU as quickly as possible, because we found that for many things, the current limitation really is the slow hardware. So if we can make another jump to a remote server,
right,
then we can possibly improve the performance.
So that would even potentially include that you could use RDMA to transfer the user data then directly to the application buffer of the client side, right?
Yes, yeah, exactly.
Okay, cool. Thanks.
Thank you for that.
Yeah, maybe just one comment from my side is that what Bernard mentioned with RDMA here is that the cool thing is, I think that you don't even have to touch the buffer one time from the DPU side when you do RDMA. Basically, the whole DMA from the host to the DPU can be done in the background asynchronously without CPU involvement of the DPU. And then you can basically directly ship out these buffers via RDMA without ever touching them from the ARM CPU, because basically as soon as you touch them on the ARM CPU side, you basically have lost in terms of performance, at least on the second generation Bluefields. I think on the newer generation it's probably much better. They also have more memory bandwidth available, but on the old ones, that's the best case scenario. And that's, by the way, also what is done for NVMe over Fabric. When they have a local NVMe emulated NVMe device, it never goes through the ARM core. Only the control path goes through ARM core.
Cool. Good observation. Thank you. Roland has a question. Can DPFS RDMA directly from host buffers without DPU DRAM bandwidth being a bottleneck?
As far as I'm aware, no. What the NVIDIA DPU library does is it first has to DMA the host buffers to the DPU itself, and then only then it can do RDMA.
In theory, it would be possible, but as Peter Jan said, I don't think it's currently done this way.
Yeah,
or there's an option to do it this way.
In theory, it would of course be possible to do this, but that's not what the current solution from NVIDIA supports.
Which makes me ask, of course, the question, is that being considered, or is that something we can talk about?
It is something we consider, but for the sake of scope and time, we haven't delved into that deep because yeah, that would require us to delve deeper into their code base, which we would rather not.
Fair enough. No, that's fair. Totally fair answer. Thank you. Okay. Are there any other questions for Peter? Okay. Well, thank you very much. Thank you very much. Good talk.